at this kind of diagram with all of our different energies, we could go through and label each of these. We start at the first energy level, so we called that energy level 1. The next energy level up we called 2. The next one, really creative. The next one, I don't have yellow. 4, 5, 6, so on, right? Officially up to 7. Can we go higher? Yes. Theoretically, we could. Do we go any higher? No. No. Why?
That's unstable.
It's so unstable we don't actually form those at those levels. We don't have to worry about it because how many rows does our periodic table have?
7.
7. So there it is. So we don't have to stress about higher than that. As we move up to a new energy level, we get a new type of orbital. With a new type of orbital, we get more orbitals. Okay? So starting at the first energy level, we only have one type of orbital. What was that type of orbital? A sphere, which we called S. Okay. When we moved up to the second energy level, you'll notice that it is now branched into 2 types. Okay. The first type is a repeat of the one below. So that first orbital, represented by a line, is S. And good classification there, you added 2s. Why 2s? It's in the second energy level, so it is a different type of s orbital. It is slightly larger than the 1s. So we start to string along this information so we know what energy level we're at, what orbital type, and then we'll add in how many electrons are there. The next energy level, or the next type of orbital was our p. Because we're at the second energy level, we only get 2 types. Okay, so what's our next orbital? We move up to our third energy level, and we'd be at our 3s. And the next energy level would be, or sorry, the next 3p, and then 3d, etc., all the way up. Okay. So now, what could we do with this information? Well, what we're trying to do is describe where the electrons exist for any atom. So let's pick one. Hydrogen. How many electrons does hydrogen have? 1. How do you know a hydrogen atom, written like that, has 1 electron?
Because it has 1 proton?
Sort of.
Because it's neutral.
Why is it neutral?
Because we don't see any charge.
Upper right-hand corner, what is written? Nothing. What is it represented in the upper right-hand corner? The charge, the balance of your protons and electrons. Well, if your charge is 0, your balance of protons and electrons must be equal to each other, which means our protons equal our number of electrons. Hydrogen has how many protons? 1, which means there is 1 electron for a hydrogen atom. According to my whole orbital diagram that we've got drawn here with all these different energy levels, where does that 1 electron go? Okay. Why do I put it in the 1s? Why do I put it in the first energy level?
It's more stable.
Why is it more stable?
Closer.
Closer to the nucleus works. That actually gives me an explanation that I can't work with. Lower in energy. Okay. Why is it lower in energy? It's closer to the nucleus. Okay. Everything is striving for as neutral as possible. So if we can get our electron closer to the nucleus, that can now cancel out the charge of our nucleus and our electron. We end up closer towards a more neutral structure. So we could go through and say, well, I've got an electron in that 1s orbital, and I can show my electron. You'll notice I've tagged a little arrowhead on top of it. That arrowhead is supposed to represent the spin. Okay? Not a big deal for you guys to stress about. Okay, so let's get rid of the arrowhead and just say there's 1 electron, and we'll make it an electron. It's purple, just showing that I have 1 electron there. I now have hydrogen. What if I made this more difficult? We'll start simple. For a helium atom, how many electrons does a helium atom have?
2.
How do you know it's 2? How do you know it's 2? It is neutral. In the upper right-hand corner of our formula here, what do we have written? do not have a 2 written there. Otherwise, you would see a 2 written in the upper right-hand corner of my formula. What do I have written there? Nothing, which is the balance of the protons and electrons. How many protons does helium have? 2. So if I take my protons and we subtract the number of electrons, this must equal an overall charge of 0. What do the electrons have to be? 2. Where's the first electron go? The very first energy level. Why? Lowest in energy. Where's the next electron go? Okay. Why do we put it right next to it? Thought electrons repelled each other. 2 can be in the same orbital because of our spin states. Again, don't need to know a whole lot about the spin. You need to know that every orbital holds 2 electrons. So I can put the second electron in that s orbital. All right? Questions? Nothing yet? Okay. Let's try again. Let's switch this now to, because you guys seem to do pretty well with that, let's go to carbon. How many electrons does a carbon atom have? 6, because it's a neutral molecule, the balance of protons and electrons must be the same. So I now have to put 6 electrons into my orbital diagram. Where's the first of those 6 electrons go? The 1s. Where's the next one go? 1s. Where's the next one go? 2s. Next one. Still the 2s, lower energy. The next one? 2p. How many electrons have I drawn? 5. How many do I need? Where's the next electron go? Okay. So 2p is correct, but now which 2p? It'll go to the second one. We won't fill the same level. Why? Lower energy to be unpaired than to be paired. Okay. This is an important distinction to make, particularly when we look at atomic size. Okay. So we've now drawn our diagram for carbon. Could we now do it for cobalt? Yeah, all we do is draw the whole same process out and start putting electrons in. If I asked you to do that for 4 elements on your exam, how happy would you be with me? Okay. You're going to have to draw a whole lot of lines, a whole lot of labels. That's a lot of work. Can we simplify that? Sure. What we will simplify it to is now just saying, instead of having to draw out the 1s orbital, I'll just say 1s. Within that 1s orbital, how many electrons are there? 2. Where can I specify that information? The upper right-hand corner, just like we specified on every other structure, our balance of electrons and protons, we're putting in the upper right-hand corner our number of electrons. How many electrons went into the 1s orbital? What's the next orbital I filled? How many electrons did I put there? 2. What's the next orbital I filled? 2p. Now we run into an interesting one. Okay. How many electrons can fit in a single 2p orbital? 2. So if I write 2 here, does that really reflect what I just drew? Not quite. Okay. So I could go through and say, well, really I've got 3 2p's. One of them has 1, another one has 1. That gets really tedious to have to label each of those orbitals, so what do we condense that down to? We condense that to 2p2. Okay. I now have the electron configuration for carbon. 1s2, 2s2, 2p2. Okay. How many electrons can the p orbitals hold? So it's a slightly different question. I said the p orbitals, that's all of our p orbitals. at an individual energy level, how many p orbitals are there? 3. Each of them holds 2 electrons, so I could have 6. Why didn't I not just put 6 electrons directly into the 2p orbitals then?
Because it's your levels.
It's a different element. Energy level.
Energy level. You must put your electrons at the lowest energy first. Okay? Then you start adding electrons in as you move up higher in energy. What we've just done is now an electron configuration. Okay? And we've looked at the big long version with all of our orbital drawings drawn out, and we've also looked at a shorthand version. Both of them are ultimately representing the same thing. It just takes up vastly different amounts of space when we go through and write it as the line. Okay? What if I went through and did, say, another element? Let's erase everything here. Let's pick sulfur. And I'm going to need more space than that. How many electrons does a sulfur atom have? 16, because of our balance of protons and electrons. We know that molecule is neutral, because in the upper right-hand corner, nothing is written. Where's my first electron go? The 1s orbital. How many electrons can I put in there? Next electrons. Next electrons. 2p6. Next electrons. Next electrons. 3p, but a p orbital can hold 6. Why are you not saying 6? Okay. If we now total up how many electrons I would have put in there, I would have been up to 18. Sulfur has how many electrons? 16. So that 3p needs to be 4. Quick test. 2 plus 2 is plus 6 plus 2 plus 4. There's our total. Okay? We now have the electron configuration for sulfur. We could theoretically push this out for any element and go through this exact same configuration. And it will get very, very tedious. Yes?
If the rule says that we have to put the lowest energy electrons in first, couldn't we just put the last electron configuration and forget about the rest because we know that they're all full?
So we've got a couple interesting features that can come out of this. And these are kind of shortcuts behind it that you are ultimately responsible for, up to you whether you want to use them or not. Okay. Number one, of all of those electrons, which are the most likely to interact with another atom? While valence is technically correct, we haven't used the term valence yet, so I don't accept that. Which of those electrons is most likely to interact with another molecule? Why the third energy level? It's the outermost. Our outermost electrons are most likely to interact with something else, which means if I'm going to look at, say, bonding in Chapter 12, the electrons that I'm concerned about are going to be the outermost electrons. The highest energy level, notice the term level, electrons. What is our highest energy level electrons for sulfur? So 3p are our highest energy electrons, but is that the highest energy level? What was our energy level? The third energy level. Anything in that third energy level are now my outermost electrons. Those are most likely to interact with something else. Because they are most likely to interact, those are going to be the ones that we're going to use to predict bonding patterns. We refer to those as the valence electrons. What might we refer to the other elements as, or the other, electrons as? Other electrons, good call. Let's be a little bit more creative than that. They're the parts on the inside. What's inside our planet? The core. These are now our core electrons. Okay. So we've now come up with a way to name each of these things. So let's look at the core electrons. Is there an element that has that many electrons? How many electrons are in the core electron? 10. What element has 10 electrons? Neon. So really, those core electrons could be represented by neon. If I want to use this as my terminology for sulfur, I can say it's the electron configuration for neon, there's my brackets, and 3s2, 3p4. I now have a shorthand that allows me to skip all of the core electrons and I can just jump straight to the valence. Okay? You do not need to use the shorthand. You can go through and show it the whole longhand. But if I gave you, say, iodine, you're probably going to want to shift the shorthand. Just depends on the element asked. Okay. Why? Iodine has how many electrons? 53. That's a lot of electrons to deal with. So what could we do for iodine then? Pause. Any questions on what's shown up there? Okay, so let's switch to iodine then. If I now want the electron configuration for iodine, it'd be really nice to use the shorthand here. So what we'll do is take a look at iodine, find where it is on the periodic table, number 53, for those of you checking it out. Okay. We want to ignore its outermost or its innermost electrons. And we want to use the core electrons, the ones that are completely filled. Okay. Which means we will go to the noble gas. Which noble gas is closest to iodine? We might say xenon. That is closest to iodine, but that is an extra electron. So I will go backwards to krypton. That now covers everything above it. So I can now start adding electrons in. My next electron goes into our s orbital, because this was our s block. Which energy level is that? I already lost track of where I was. Which row is that? Okay. It's our 5th row in our s block. Our next electron would go into the 5s orbital, which would mean I'd be at 5s1. This one would be 5s2. Now we got a trick. We move into the d block. What energy level is our d block? It is offset by 1. This is our 4d. 4d1, 4d2, 3, 4, 5, 6, 7, 8, 9, 10. How many electrons fit in the d orbitals? 10. So we've now completely filled our d orbitals. Keep losing track of where I am. To move into indium, I would now be in which block? The p block. I go back to my normal row numbering, and that would be 5p. 5p 1, 2, 3, 4, 5. And I have my electron configuration. Okay. I wish there might be an easier way to figure out how many electrons should be showing up in that last section. Okay. We can figure this out by looking at our valence electrons. Where are valence electrons in this case? Our 5s and our 5p, which means we have how many valence? 7 valence electrons. Take a look at iodine, very top of that column. What row label do we have there? We have 17 for iodine. Roman numerals right next to it? 7. How many valence electrons do we have? I wonder if that holds true for all of them. It does. That's nice. Okay. So if we look at our columns for our S and our P, only the S and the P, we now know how many valence electrons belong to every element within that column. Okay. It can help us predict our electron configurations. Okay. But ultimately, it's just another piece of information stashed, hidden away in our periodic table. What about those d electrons? Are those part of the electron configuration? Yes. Okay, they are part of the electron configuration. They are not part of the bonding structure for iodine as Lewis predicted it. And we'll get into Lewis, okay, when we talk about him and his theory. His theory came down to 8 electrons, which means he only took into consideration which orbitals? S and P. Okay. Questions on our electron configurations?
Why don't you go to 5s2 and go back to 4d?
Okay. So we run into this interesting dilemma. From 5s, we would expect the next highest energy would be 5p. Why did I drop down to 4d? Okay. Whoa, come back here. I wanted this. Okay. Let's go through and add the 4th energy level. The 4th energy level splits into 4 subsections. There's 1. There's our P. There's our D. 1, 2, 3, 4, 5, 6, 7. There's our F. What is the difference in energy between this orbital and this orbital? They are darn close to each other. And so what we notice ends up happening is as we get further or higher in energy, all of those energy levels start to stack on top of each other. And now our electron gets to decide, where does it want to go? Okay? So here's where we run into an interesting dilemma. So let's think about this kind of abstractly first. Okay? In your real life experience, imagine the most perfect person you can. Stop staring at me. Okay. The most perfect person you can imagine. You find them incredibly attractive, anything you want like that. Okay? Now put a mirror right through the middle of their face. Guess what you notice? They're symmetric. Okay? Nature strives on symmetry. Symmetry is a nice, beautiful, balanced thing. Guess what happens when we go to electron configurations? Symmetry shows up as well. Which is more symmetric? 1 orbital half filled or 5 orbitals with only 1 electron in it? Okay. Those 5 orbitals are now massively unbalanced. The 1 orbital with only 1 electron in it is a little bit more balanced. So our electron now has a choice between our energy level starts to become very, very small. When we move from 1s to 2s, we're looking at a big difference. When we start to level it out between our 4s and our 3d, that energy difference is now very, very small. We say, okay, well, now I'm not concerned about energy. I'm concerned about how pretty I look. Well, I'd rather look pretty. So it balances out as a symmetric thing. How do we know when that happens? Well, those energy levels would have to get really, really close, and we'd have to quantify all of that energy. I'm bad with numbers. I don't want to quantify jack. Okay? So what do we do instead? We come up with some pattern to help us remember how they fill. One option is memorizing that your d orbitals are offset by 1. Okay? Which means when I get to scandium, my first d orbital, that appeared at which energy level? The 3rd energy level, even though it's in the 4th row. Okay? The periodic table is organized according to its fill pattern, not according strictly to our energy levels. Okay? It works for rows 1, 2, and 3, because in rows 1, 2, and 3, we skip the d orbitals. We don't fill yet. Okay? So you can memorize that pattern is there, that your d orbitals are offset by 1 energy level. The other thing that you can go through and do is this electron configuration diagram, which those of you that have come to office hours, I've drawn out a whole bunch of different times. Okay, and we just write, okay, in our columns, starting with 1s, well, there's no other orbitals, so it's just 1s. Then we do the next row. It's 2s, 2p, no other orbitals. Move up to the next row, 3s, 3p, 3d. And you continue to put in all your orbitals. Okay, officially for the 4, we have the 4f out there. And I don't have any space, so I'm just going to write it over the top of itself. Okay. How do we use this to determine our fill patterns? Well, we start on the diagonal. We go up 1s and we stitch backwards. Go back through the bottom of our material and we stitch back up to the 2s. We go back through our material. Those of you that sew, maybe this makes more sense. Okay. And then you go up to the 2p, which then fills to the 3s. You stitch back through the material and you go back up and you encounter the 3p. What's the next orbital you encounter? 4s, not the 3d. You don't encounter the 3d until you stitch back down through your material and come back up into the 3d. Is that confusing? Yeah. That's why it's a lot easier just to remember that your d orbitals are offset by 1. Okay? But that gives you your fill pattern. Okay? And it gives you the appropriate energy levels and when you put them in. Okay? We already talked about valence electrons. Do we need to do another example? Once? Twice? Okay. We mentioned this already. We can use the periodic table to help us configure where our different energy levels are located. The first 2 columns are referred to as the S block, because if we look at their electron configurations, what will you find? Their valence electrons are all in the S orbital. Okay? Regardless of where they fall within the columns, they're in an S-type orbital, or within the row. Okay? If we move to, say, our transition metals in between, if we look at the valence electrons, we'll notice that we fill the d orbitals, which means that is referenced as our D block. If we move to the last one, or really the last one as far as you're concerned, if we look at the electron configuration for all of those, our absolute highest energy is in the p orbitals. We now have the p block. Okay? So it can help you determine your electron configurations. Okay? Yes?
Will we not be using that one?
You won't see the F block. Yeah. If for some reason you see a question in your textbook, you can ignore it. We don't need to worry about the F block. Why do we not worry about the F block? It's not so much that they're too high. Theoretically, we could make it do with anything. Number one, they're all unstable, very radioactive. Almost all of them are radioactive. Generally not a good idea to have students work with those. Okay? So that's a pretty good reason. The other big reason, you should notice about half of them, a little bit less than half of them, are all white. What is that? They're synthetically made, which means even if we wanted you to work with them, it's stupidly expensive to get a sample big enough for you to work with. Okay? So it just doesn't make sense to really look at the electron configurations for those. You're more than welcome to go through and do it. Maybe in 151, an instructor will throw one at you like that. Okay? You won't see that here. For the most part, we will sit in the S and the P's. For this class, the D block might show up as one possibility. 151, you are absolutely responsible for the D block. Okay? Which means we are now starting to drift back into Chapter 5. When did we leave Chapter 5? And don't tell me Tuesday. Why did I switch? I went from Chapter 4 into Chapter 5, and then I went from Chapter 5 back to Chapter 4. What was the last thing we talked about in Chapter 5? I know that was forever ago. What about the periodic table? It was a trend in the periodic table.
Charges.
Not even charges. Atomic radius was the last thing we talked about. What was our trend for atomic radius? As we went down a column, what happened? Got bigger. Why would it get bigger? More electrons. We're going to higher energies. If we look at our electron configurations, we're in a higher energy level when we move down a column, which means our electrons are necessarily further away. So our atom gets bigger. The trend that was weird is when we move left to right in the periodic table. What happens? It gets smaller. But what happens to the number of electrons as we go left to right? It increases. But isn't that what happened when we went down a column? Why is it all of a sudden getting smaller? I think that's an interesting question. I think that's so interesting, that'll be on the quiz. 2, how many electrons fit in the d orbitals? 10. You got to be very careful when you read this question, because I've screwed it up a few times too. 1p orbital, not plural. Doesn't matter. Any orbital holds 2 electrons. Fit in the d orbitals, see the s? We're now referring to all of the d orbitals. In all of the d orbitals we get 10 total electrons. Okay? What was that? Question 4. Why does atomic radius increase down a column? Has nothing to do with mass. Has nothing to do with protons. More electrons. The electrons are what contribute to size. Protons do nothing for size. They are all jammed into a marble inside the superdome. You increase the number of electrons. You move down a column, more electrons, bigger. Atomic radius decreases from left to right. This is a bit odd. Because what are we doing? We are adding electrons and protons. But we're adding electrons. Either way, we add electrons and protons. When we go down a column, we say, yeah, it's getting bigger because we added electrons. When we go across a row, doing the exact same thing, it appears that we're getting the opposite trend. Okay? So here's a question that's going to actually reference some future slides here. How many people actually care to know what the trend is, or why the trend is the way it is, as opposed to just knowing the trend? I don't care if it's on the test or not. We're roughly 50-50. Okay, so when we hit future slides, for those of you in that 50-50 category may want to talk to me about the why on different trends. This trend I'm going to tell you the why on. When we move from lithium to beryllium, lithium's electron configuration, valence electron count, would be 2s1. When we move from lithium to beryllium, it becomes 2s2. Actually, let me change the spacing here. We move from lithium to sodium, what does it become? 3s1, right? So when we go from lithium to sodium, we are increasing the number of electrons. Where are the electrons going? A higher energy level, which means they are further from the nucleus. When we go from lithium to beryllium, where's the electron going? The exact same energy level, which, if anything, would suggest the size should not change, because we're putting the electrons into the exact same energy level. It shouldn't get any bigger. Right? It should stay the same. Our trend is actually that it decreases, though. Why might it decrease? What else changed as we went from lithium to beryllium? The number of protons. So my electron is going into the exact same distance away, but my nucleus is now getting stronger. What happens to the electron? It gets pulled just a little bit closer, which means the size gets smaller. Pretty cool. How do we determine all that? From the electron configurations. Without an understanding of electron configurations and where our electrons can exist, this trend makes no sense. You are responsible for knowing the trend. The why on this one gets a little bit tricky. It might become an extra credit question. Okay? There's a hand. Was it you? After? Okay. So, our atomic radii, if we go through and take a look, we'll notice that our size decreases as we go left to right, and that's because we're getting a larger nuclear charge and the electrons are going in at the same energy level. When we go down a column, it gets bigger. We are increasing the nuclear charge, but at the same time, we're putting the electrons further away. That is why it gets bigger. So you're seeing two competing features kind of counteracting each other to get the different trends. You're responsible for the trend, the why is less important. Questions on that? Okay. Which brings us to the next big one. This is another trend that we can pick out of the periodic table. Guess what allows you to predict your ionization energies or your ionization energy trend? Electron configurations. Okay? So those of you that raised your hand and wanted to know why on the trend, look at your electron configurations and see if you can predict the trends for your ionization energy. If you have an issue predicting it, that's when you should talk to me. The ionization one is a little bit trickier than our radius because there are exceptions to the ionization energy trend rules. Or it's not a rule. Whatever it is, the trend. Okay? You will not get tested on the exceptions. Okay? I may ask you to explain the exception as an extra credit question. So what is our trend, or what is ionization energy? Ionization energy is the energy required to remove an electron to the vacuum. So we're taking an electron from a ground state. So if we looked at our electron configurations, our diagram, right, we had something along these lines, and it got closer and closer to the vacuum. The energy required, say, to remove a 1s electron. Okay? It is now the distance between our vacuum and here. This is now the energy required to remove a 1s electron. That would be the ionization energy for hydrogen, element with one electron. What happens if we say move to lithium? We would have an electron in the 2s. Would I expect the ionization energy to get bigger or smaller? Smaller. Why? You're higher in energy, you're closer to it already being removed. So when we look down a column, what happens to the ionization energy? It gets smaller. If we go through and look at our trend, and of course we can change all of our prefixes on here, it increases from bottom to top because you're going closer to the nucleus, lower in energy orbitals. What happens as you move left to right? You're now changing where your electron is located within it, and we also see it increase as we go left to right. Why? Your nucleus is more positive. The more positive the nucleus, the tighter held the electrons, the lower energy they are. Yes?
So that's why nuclear reactors can generate so much electricity is because their energy levels are so high.
Nuclear reactors have nothing to do with electrons. They have everything to do with nuclei, the nucleus. Hence we call them nuclear reactors. Okay? You're looking at what's happening to the nucleus, not to the electrons. Okay? Those are your big trends. We could go through and look at, of course, your exceptions. These are always said in general, and that's because there are big exceptions to these. Those exceptions are all predicted by looking at the electron configuration and what we were talking about earlier, symmetry. The more symmetric your starting position, the more pretty it is. If you were to rip an electron away, it becomes unsymmetric and ugly. Do we want to become ugly? No. So what happens to the ionization energy? It changes. It goes up because we don't want to remove that electron. So when we look at our trend, that's what you're seeing here with this plot. You're looking at the change in atomic number on the x-axis. So we would start with hydrogen. We add one electron. What happens to our ionization energy? It increases. Why? We have a larger nuclear charge holding the electron. The next one, you'll notice we move to lithium. And so what they're trying to show is the general trend as you go across your periodic table, what happens to the ionization energy? Gets bigger. What happens as we go down a column, say from hydrogen to what's next? Lithium to sodium to potassium. What happened? Hydrogen, lithium, sodium, potassium, rubidium, cesium. What happened to it? It decreased. Matches our trend. The tricky ones, I'll point out for those of you trying to figure out your why. Probably the easiest one to look at is in here. You're looking at nitrogen versus oxygen. Nitrogen has a higher ionization energy than oxygen. Another tricky one for a similar reason. Beryllium versus boron. Your why reason comes from your electron configurations. Draw the electron configurations for those and predict. Okay? Why would those ionization energies be different? Okay? There's a big hint on this. Boron is the reason that it's lower. Nitrogen is the reason that it's higher. Okay? Questions on ionization energy? Okay. What does the charge become when we look at ionization energy? If we rip an electron away from the structure, all of our molecules become positively charged. We lost an electron. Minus a negative charge is positive. Not in your textbook. In fact, the next two slides, I think, are not in your textbook, but it's important to reference. The other thing that will pop up in 151 is this concept known as electron affinity. Well, ionization energy was removing an electron. What is electron affinity? Grabbing an electron, doing the opposite. All right? We'll see that we end up with similar ideas within trends. Okay? Again, you're not responsible for the trend here. You're not even responsible for knowing electron affinity, but I'm bringing it up as an important topic. One of the things that we'll find is our ionization energy for our metals is always low. Okay? What charge do our metals typically become? Positive, because it's really easy to get rid of an electron. When we look at electron affinity, we kind of change the concept around on this. What charge does our atom become if it accepts an electron? Negative. What do we end up finding? Our metals do not want to accept electrons. Okay. Why? What charge do metals become? Positive. So their electron affinities are virtually nil. They don't want to accept more electrons. Yes?
Where is electronegative? Because I know in the video that...
So the reason why we mention electron affinity is that what we are trying to do is to now predict the ability of an individual element to either give up its electrons to another atom or to take electrons from another atom. That is the balance of our electron affinity and our ionization energy. Whoops, please reconnect. This is important. Good. That is electronegativity. Okay. It is the ability for any atom to take bonding electrons from another atom. So if we put two atoms near each other and they start to share electrons, the more electronegative the element, the more likely it will take the electrons away. If it takes the electrons away, what charge does it become? Negative. Where's our most electronegative element? Upper right-hand corner, fluorine. Our next most, oxygen. Where are all of our most electronegative elements? All in the upper right-hand corner, excluding our noble gases. Everything in our upper right-hand corner are what kind of materials? Non-metals. If we take a look at our least electronegative, they're metals. What happens when you put a metal near a nonmetal? The nonmetal steals the electrons and it becomes charged. What charge? Negative, which makes it an anion, and the other one, the metal, would become a cation. What type of bond do we have between a metal and a nonmetal? Ionic. There's nomenclature. Okay. It's coming out of the balance of what's happening within those. So if we tried to predict something about charges or electronegativities, we're coming out of electronegativity. This concept is stupidly important. Arguably anything in organic chemistry can be predicted based off of understanding electronegativity. Huge. Okay. Really all you need to know is what the trend is. Upper right-hand corner, most. Lower left-hand, least. This trend's the opposite of the metallic characteristic. Those of you that watched the video, I made a quick judgment change because my video bases Lewis structures off of electronegativity. Well, you didn't know electronegativity at the time you watched the video. So I referenced metallic character. Okay, because they go directly opposite each other. It works. Yes? You'll notice that we get all sorts of weird crap happening in the D block. What did we say we were going to do about electron configurations for D block elements? Not worry about them. Why? All sorts of weird stuff happens in the D block. Okay? Particularly as an organic chemist, what do I do with D block elements? I ignore them. Okay? Because too much confusing stuff happens in there. It's way too difficult for me to understand. Okay? This is why organic chemistry is cool, just as a little precursor for anybody that actually joins organic chemistry. We made you responsible for most of this periodic table. Let's take a look at what organic chemistry looks at.
I should have took that class.
And actually, I screwed that one up. That's organic chemistry. Okay. We keep our focus in there. And arguably, actually, we can get rid of the fluorine, too. Okay. That just means we make it more difficult. There's other aspects to it. Because you bring in the other elements, it makes it a whole cluster mess. Okay. So, electronegativity is important. The next part about this, we already started to talk about our ionic charges. Okay. You are responsible for knowing the charges. Stupid slides or images taken from the textbook. You are now responsible for the charges, all of the charges on this slide. Okay? And let's see if I can add them in here. Zinc, cadmium, and silver. That's a G, not a Y. You need to know every single one of these charges, which means when you go through and name a compound that uses any of these elements, okay, you do not specify charge. Okay. What if you use a compound or name a compound that uses a different element? You need to specify the charge. Comes back to nomenclature. Is there an easier way to memorizing these charges? Kind of, sort of. You could just go through and on your periodic table, as soon as you get it, first column you say +1, next one, +2, next one. Ooh, that one's tricky. We'll come back to that one. Why is it tricky? Hey, guess what? Look how many elements we tell you to memorize. Because it's tricky. Next one, -3, -2, -1. Our charge all of a sudden changed. Take your periodic table and envision it like a cylinder. Okay, and if we offset it just a little bit, all of our elements are trying to look like the noble gases. Why were the noble gases unreactive? Why are they stable?
All of the that one levels of the electrons are full.
Our electron configuration, all of the orbitals are completely full, which means there is no place to put an electron. So it can't accept electrons from another element. Because it is full, it doesn't want to give up electrons. Okay? Which means all of those are virtually unreactive, which means they don't react. They're super cool. They are the most neutral, lowest energy thing we can get. Well, what is the rest of the periodic table trying to do?
Like
become neutral and low energy. So every other element on the periodic table is doing whatever it can to look like a noble gas. Well, what makes up a noble gas? What makes up helium? Proton and neutrons and electrons. Okay? If we change the number of protons, what happens? Different element. So we can't change the number of protons. We could theoretically change the number of neutrons, but changing the neutrons just makes it an isotope. It doesn't make it any more looking like our noble gases. The only thing left, I'm going to have to count that way. The only thing left is the number of electrons. So we can change the number of electrons around an individual element to make it look like the noble gases. Envision it like putting on different clothes. Okay? We're all trying to look rich, so we buy fancier clothes, because then people think we have money and we'll become cooler. Okay? Or we do the opposite, because we're like, F you.
Is there a way that we could force an electron into one of the noble gases? Like, say,
Can we do all sorts of crazy stuff to the noble gases? Absolutely. Not easy, but we can do it. Okay? So let's take a look at fluorine. What does fluorine need to do to look like a noble gas? It's going to look like the closest noble gas possible, so neon. Well, neon has 10 electrons, fluorine has 9. What does fluorine need to do? Accept one more electron. It now has 10 electrons and how many protons? 9. What's our balance of charge? -1. So fluorine becomes a -1. What happens to oxygen? Oxygen comes in with 8 protons, 8 electrons. It would be neutral as an oxygen atom, but it wants to look like a noble gas. Which noble gas is closest to it? Neon. What does it have to do to go from oxygen with 8 electrons to neon with 10? Gain 2 more electrons. So we would have how many electrons? 10. Which means our charge would be -2. Okay. Within our formulas on this, we're taking the number of our protons times the charge on a proton. What's the charge on a proton? +1. We will add this to the number of our electrons times the charge on an electron, -1. What does this have to equal? Nope. Our charge. So if we're trying to predict something about the charge on an individual ion, okay, if it's one of the ones we're required to memorize, we can come up with a prediction. Sulfur should try and look like which noble gas? Argon. Sulfur comes in with how many protons? We got 16. Charge on a proton is +1. I can't change the number of protons to look like argon, but I can change the number of electrons. How many electrons would I need to look like argon?
2 or 8.
Total of 18. The charge on an electron is -1. What does my charge equal now? Punch it in the calculator and we get -2. Why do we not have you memorize anything for carbon? Which is the closest noble gas? Neon or helium. To look like neon, what does carbon have to do? Gain 4 electrons. To look like helium, what does it have to do? Lose 4. It's an even balance. There is no clean way. There is no easy direction to go. So what happens with carbon? It can technically hold any one of the spectrum from -4 to +4, which is why we don't have you memorize it. Okay? When we move to aluminum, okay, I know it's a little bit trickier, but boron follows suit. Which noble gas is closest to aluminum? Argon or neon? Neon. What does aluminum have to do to look like neon? Lose 3 electrons. To look like argon, it has to gain 5. Which is easier? losing 3. Because it is easier, aluminum and boron will hold the same positive 3 charge. Okay? Both of which can be calculated out of that little equation that we've got at the bottom. It's just the balance of our protons and our electrons.
So you take a path of least resistance.
Path of least resistance. Okay? Just like you, chemistry does the same thing. You may not always see it as the least resistance, but it is. Okay? Questions on that? Ultimately, you are responsible for knowing the charges, okay, on those ones up there. Some of them you can predict. Group 1, Group 2 goes off the noble gases. Why is zinc, cadmium, and silver those charges? Good question. You don't need to know why on those. You just need to know what their charges are. Okay? Questions? Okay. Chapter 4, things that we covered. There are some cool scientists. Cool scientists like Thomson, Rutherford, Curie, Millikan, Dalton. You should know why those scientists were cool. What did they discover? We also identified subatomic particles. You'll notice I'm only listing protons and neutrons at first because electrons were the second half, ultimately, of Chapter 4. You're responsible for knowing their charge and their relative mass. Relative charge and relative mass. Wave nature of light gets us to this whole concept of continuous versus discrete. Okay? Why was discrete important? That told us we had electron orbitals. If we had continuous spectrum for our light or our atomic light spectrums, we end up not getting energy levels. Bohr is a discrete gentleman because no one laughed. Thank you. I appreciate that. I thought it was funny. Okay. He was responsible for identifying our discrete energy levels, our distinct energy levels, so that we stepwise through our electron configurations. Which gets us to orbitals. Orbitals are where our electrons exist. Okay? We now have electrons. You're responsible for knowing their mass and their charge. Relative charge of an electron? -1. Relative mass? 0. You're also responsible for the electron configurations. This is a combination of your orbitals and your electrons. Most important out of that is identifying your valence electrons, which is what you need to do Lewis structures. Chapter 5. We talked about some periodic table stuff, predictions of trends within your periodic table, electron orbitals, chemical and physical properties, atomic radius, ionization energy, and ionic charges. Did you mention Lewis structures starting in Chapter 5? You'll notice Lewis structures are not being mentioned in Chapter 5 because I think the Chapter 5 reference of Lewis structures is stupid, frankly. Okay? Which now gets us in the last 30 seconds, a quick intro, really quick intro, into Chapter 12. Electronegativity is an important aspect to be looking at. You need to be aware of using it when trying to predict bonding properties. What makes a bond? I bring 2 nitrogen atoms near each other. How do I know I now have a bond? It's the sharing of electrons. That's what causes a bond. Okay? Would I predict all bonds to be the same? Okay? If I change the atom, that changes the electrons, which should then change the nature of how they share their electrons. So I get different types of bonds coming out of this. Your textbook references these as 2 big subcategories. Ionic bonds, which is typical of metals and nonmetals, and then covalent bonds, which is 2 nonmetals. Are there variations within this? Abso-freaking-lutely. Okay? But those are our 2 primary categories. You've seen those 2 primary categories before because you saw it in nomenclature. So being able to recognize a structure and classify it as either ionic or covalent helps you then go through and do your nomenclature. Right? Not all covalent bonds are the same. For instance, if we take a look at bonding hydrogen to oxygen, we get what compound? Water. If we bond hydrogen to, say, chlorine, we get hydrochloric acid. Are those compounds the same reactivity? No. Why not? Because their bond chemistry or their bond nature is distinctly different. Okay? They are still both technically classified as these covalent bonds, but they have separate subcategories coming out of it. Within your ionic bonds, you've got positive charge and negative charge. I know. We will pick up with all those slides I just whipped through real quickly on Tuesday. Really what I want you to look at is within Lewis structures, this is your rule set. The most important rule to be following, in my opinion, more so than anybody else's opinion, and I'm always right. I do appreciate the laughter there. Add electrons to your most electronegative atom first. Okay? That rule is what is broken in Chapter 5. Right? Always add your electrons to the most electronegative atom first to satisfy the octet of 8 electrons. Why 8 electrons? S and P orbitals hold 8 electrons. There's your octet rule. Thanks for your patience.